Okay, let's unpack this. We've gotten really used to magic.
Magic.
Yeah, technological magic, the kind we just take for granted every single day.
Right.
You type a half-formed thought into a search bar, or, you dictate a text message while you're driving, and the computer just, it gets it.
It feels seamless.
It does. It feels like the machine can read your mind,
Hmm.
but we sort of forget that these systems are usually trained on the good stuff.
Right. They're raised on a diet of perfection.
Mm.
Millions of Wikipedia articles, professionally edited books, the New York Times.
Exactly.
Yeah.
It's clean, perfect, standardized data. It's like learning to drive on an empty, sunny racetrack.
I like that.
Everything is predictable, the lines are painted clearly. But what happens when you take that self-driving car and you drop it into rush hour traffic in a city where, I don't know, no one follows the road signs?
That is the perfect analogy for what we're diving into today. Because real life isn't a racetrack.
Real life is messy.
So messy.
We're looking at a fascinating study by M. Pilar Valverde Ibanez that asks a really fundamental question about AI. She essentially performed a stress test on these language algorithms.
She did. She took standard computer tools designed for perfect Spanish, and she fed them essays written by Japanese students who were just learning the language.
We're talking about broken language here.
And I don't mean that in a bad way, but, in a linguistic sense.
Sure.
Creative grammar, invented words, spelling disasters, and the big question, the mission of this deep dive, is simple. Does the machine crash and burn? Or is it smarter than we think?
I love this setup. You have these Japanese students, they're at an intermediate level, B1 or B2, I think.
Yeah, that's right. So they know enough to be dangerous, but they're definitely not fluent.
And they're writing these essays in Spanish.
And the linguistic distance there is huge. I think that's important to emphasize.
That's what I was thinking. I mean, if I'm an English speaker learning French, okay, that's a hop. But Japanese to Spanish...
Okay. That's an ocean. It really is. Everything is different. The alphabet, obviously, but the logic is different.
How so?
Well, in Japanese, the verb usually comes at the very end of the sentence. In Spanish, the structure is way more flexible. So when a Japanese speaker tries to write Spanish, the mistakes they make aren't just random.
They're structural.
Exactly. They are trying to map their native logic onto a completely different system.
So we have this Frankenstein text, and the mission is to see if standard computer tools can do part of speech tagging on it. Before we get into the results, what is that exactly? Part of speech tagging.
It sounds like 7th grade English class, right?
It really does.
But for a computer, it's the absolute first step in understanding anything. Before it can get the meaning, it has to label every single word. It has to say, table is a noun, run is a verb, blue is an adjective.
Which sounds easy for us. I don't even have to think about it.
Easy for a human, surprisingly hard for a computer. Because words are slippery. Take the word run. Is it a verb like I run every morning?
Or a noun, he hit a home run.
Exactly. The computer has to figure that out from context. And if the context is full of grammatical errors, well, you can see how it might get confused.
So this study takes two specific tools and throws them into the ring. Who are our contenders?
So we have two different philosophies of AI here, which makes it even more interesting. The first is a tool called Freeling.
Freeling sounds very open-minded.
It sort of is. Freeling is the statistical approach. It uses something called an HMM trigram model.
Okay, hold on. HMM trigram, let's break that down. No PhDs allowed.
Right. Think of Freeling as a gambler. It plays the odds. Trigram just means it looks at 3 words at a time. It looks at the 2 words that came before, and it places a bet on what the third word is.
So it's just guessing.
It's an incredibly educated guess. It's been trained on massive libraries of Spanish text. So it knows, statistically, that if it sees the and then big, there's a 99% chance the next word is a noun.
Okay, so Freeling is the gambler counting cards. I've seen this pattern. I'm betting on noun. Who's the second contender?
The second tool is Hispal, and Hispal is the opposite. It's a rule-based parser. It uses constraint grammar.
So if Freeling is the gambler, Hispal is the librarian.
Or the lawyer, a very strict by-the-book lawyer. It has a massive rule book and a giant dictionary. It doesn't guess. It looks the word up.
So it's all rules.
All rules. If this word ends in O and follows a verb, it must be X, unless Rule 45 subsection C applies.
Okay, so we have the gambler versus the lawyer, and normally on perfect text, how do they do?
They are incredible. On native Spanish, Freeling hits about 97% accuracy. Hispal is almost 99%.
99%. So that's the baseline, the gold standard. The expectation then is that with these essays, those numbers should tank.
Exactly. The gambler's patterns are broken, and the lawyer's rules are broken.
Let's talk about the data they used, the Korean corpus. What were these students actually writing about?
I love this part because it reminds you there are real people behind the data. The prompts were things like, my holidays, my first impression of Spain.
The usual stuff?
Yeah, but my favorite prompt was, what I would do if I were invisible.
Oh, man. I can see the grammatical nightmare from here. That requires the subjunctive mood, conditionals.
It's a minefield for a learner. If I were invisible, I would go.
That is so hard. I still mess that up.
Exactly. And remember, these students are Japanese native speakers, so they might be inventing words or using a catechinized version of a Spanish word.
So the stage is set. We have the gambler and the lawyer facing off against these essays. I'm expecting a total bloodbath, maybe 50% accuracy. What happened?
This is the big reveal. They didn't crash.
Really?
They were surprisingly, remarkably resilient. Freeling, our gambler, came in with a precision of 92.6%.
That's barely a drop. It's like a 4 or 5% drop.
And Hispal, the lawyer, it hit 95.0%.
95%. That is almost native level. It's an A grade.
It is incredibly high. And the study even did a control where they manually fixed the essays and ran the tools again. The precision only went up by about 3 percentage points.
Wait, so this implies one of two things. Either the students were writing much better Spanish than we thought, or the computers are much smarter.
It's a bit of both, but it points to a really crucial distinction. It's the difference between form and function. This is the core insight of the paper for me.
Okay, unpack that. Form versus function.
So there's learner error, where the student makes a mistake.
No.
And then there's tagger error, where the computer gets confused.
And they aren't the same thing.
Not at all. The study found that just because there is a learner error, it doesn't mean there will be a tagger error.
Can you give me an example?
Sure. The paper highlights a great one. A student wrote, muchísimos habitaciones. They were trying to say a lot of rooms.
Okay, my high school Spanish is kicking in. That's wrong. Habitaciones is feminine. It should be muchísimas with an A.
Correct. The student used the masculine ending. That is a clear grammatical error, a gender agreement error.
Right. Your teacher would circle that in red ink.
But when the taggers looked at it, they both correctly labeled muchísimos as a determiner.
So the computer basically said, okay, I know you messed up the gender, but I can tell from its job in the sentence that you're trying to quantify the noun, so I'm calling it a determiner anyway.
Precisely. The computer recognized the function of the word, even though the form was wrong.
That is surprisingly forgiving. It's almost human-like.
It is. The study found that both taggers correctly identified the part of speech for about 65% to 70% of the words that had learner errors in them.
So the grammar police part of the software is actually pretty chill.
It shows that both models are robust enough to handle what linguists call distribution morphology mismatches.
That's the fancy term for it?
It is. Think about English. If you say the dog runs, it's wrong. But a computer knows runs is still a verb.
Right. It doesn't stop being a verb.
Okay, so we've established that bad grammar didn't break the machine, but the accuracy did drop. So something must be the Achilles heel. What tripped them up?
If grammar didn't break them, spelling did. Orthography. This is where the battle was lost. Spelling. Just typos. Well, it's more than just typos. In Spanish, spelling includes accents, and accents aren't just decoration. They do heavy lifting.
Okay, give me an example of how an accent changes things.
Take the word hablo. H-A-B-L-O. That means I speak. Present tense.
Right.
Now put an accent on the O. Hablo. That means he spoke. Past tense. Third person.
Ooh, huge difference. Different person, different time.
Massive. Or take esta, this, versus esta, se. If you miss that accent, you're not just misspelling a word. You're often changing the part of speech entirely.
And I imagine for a Japanese learner whose native language doesn't even use the Latin alphabet, remembering where to put that little dash is incredibly difficult.
It was a huge source of errors. And the stats here are brutal. The taggers only had about 30% precision on words with accent errors.
Wait, 30%? We were just talking about 95% accuracy.
Yeah, it fell off a cliff.
Yeah.
Because if you miss the accent, the computer often sees an unknown word. And when it sees an unknown word, the gambler Freeling starts guessing wildly.
And the lawyer, Hispel, just shrugs. It looks at its dictionary and says, not in my book. Can't help you.
So, complex grammatical gender failures. Computer says, no problem. Missing a tiny accent mark. Computer has a total meltdown.
Exactly. And there was another trap that really hurt them. Capitalization.
Capital letters.
Yeah, the Japanese learners often struggled with when to capitalize proper nouns, so they'd write Madrid or Juan with a lowercase letter.
Which makes sense because Japanese doesn't have capital letters.
Exactly. But you can probably guess who this hurt more, the gambler or the lawyer.
Oh, definitely the gambler. Freeland.
You nailed it, because its statistical model says proper nouns are almost always capitalized. If Juan is lowercase, it's probably not a name. Maybe it's a verb.
It overthinks it.
It does. Freeling's precision on proper nouns dropped to 58.7%, just because of capitalization.
It's funny when you think about it. We spent all this time in language class drilling conjugations, but for the machine, the thing that makes you unintelligible is not hitting the shift key.
It really highlights how brittle these systems can be on surface-level features. They can handle deep structural errors, but they trip over surface noise.
So it's all about the surface noise.
There was one more thing that drove them crazy, the say ambiguity.
Say ese.
Yes, the word say. It is the nightmare of every Spanish student.
Oh, I remember. It's reflexive, right? He washes himself. Se lava.
It is reflexive, but it's also reciprocal, it's impersonal, it's part of certain verbs. It's a chameleon word. It does 4 or 5 different jobs.
So how did the computers handle the chameleon?
Poorly.
Yeah.
Especially Freeling. Because the student's sentences were a bit wonky, the context was messy. So Freeling would try to guess which C was being used, and it would often guess wrong.
It overcommitted. It tried to be too smart.
Exactly. But Hispal, the lawyer, played it cool. It used a strategy called under-specification.
What does that mean?
Basically just said, look, this is a say. I'm not going to promise you what kind of say it is, but I'm marking it as a say and moving on.
Smart. Sometimes the best answer is, I'm not going to speculate further.
In the context of learner language, absolutely. By staying vague, it maintained higher accuracy.
So let's zoom out. We've looked at the battle. The computers won on grammar but lost on spelling. What does this mean for the real world? Why does this matter?
It matters because of ICAL, Intelligent Computer-Assisted Language Learning. We're moving toward a world where you learn Spanish from an AI tutor. You write an essay, and the computer grades it instantly.
Right, we see this already. Tools like Duolingo, automated essay graders.
But for that AI to give you good feedback, to say, hey, you used a noun here, but you needed a verb, it has to know what you wrote first. If the tagger fails, the feedback fails.
So the author proposes a solution. And I like it because it's not build a massive new AI brain from scratch.
No. The verdict is we don't need to reinvent the wheel. The standard tools are actually good enough. We just need to help them out a little.
What's the fix?
A pipeline approach. Since grammar errors don't confuse the machine, but spelling errors do, we just need a bouncer at the door.
A bouncer.
A pre-processing orthographic module. Basically, a really good spell checker that runs before the tagger sees the text.
So, step 1, the student submits the messy essay. Step 2, the bouncer fixes the typos, adds the missing accents, capitalizes Madrid. Step 3, the standard AI reads the cleaned up text.
Exactly. And the study estimates that if you do just that, ignore the grammar mistakes, the accuracy jumps back up to 96% or 98%.
Back to native levels.
It essentially is.
That is incredibly efficient. It's like saying, hey, computer, I won't fix my bad grammar, but I'll spell the words right, and then we're cool.
It simplifies the problem. We don't need an AI that simulates learner logic. We just need an AI that cleans up the surface noise. Once that's gone, the underlying structure is clear enough for the standard algorithms.
It really makes you think about how we build educational tech. We always want the smartest tool, but sometimes you just need simple tools working in the right order. Spell check first, then analysis.
Absolutely. It validates that learner language isn't just garbage data. It's structured, meaningful communication.
It's just a little rough around the edges.
Exactly. And really, that's what this study is about, bridging the gap between the messiness of human learning and the rigidity of computer logic.
So, to recap, we learned that computers are surprisingly forgiving of our bad grammar, but they are absolute sticklers for our spelling.
Which, honestly, sounds like some of my old English teachers. They could forgive a run-on sentence, but if you spell the author's name wrong, automatic fail.
True, but it's encouraging. It means the tech is ready to help us learn. We just need to scrub the data a little first.
That's the takeaway.
Before we sign off, I want to leave you with a thought. We've been talking about how computers process broken language. They use probabilities, the checklists. But think about us. Think about the human brain.
Okay, where are you going with this?
Well, when you listen to a non-native speaker or a toddler, they are making mistakes constantly, dropping articles, using the wrong gender, and yet you usually understand them perfectly.
That's true. We rarely even notice the errors. We just fill in the blanks.
So if a computer works by fixing the spelling first and then looking at the structure,
Hmm.
are we doing the same thing? Are our brains running a massive pre-processing orthographic module in real time? Are we unconsciously autocorrecting the world before we even consciously hear it?
That is a deep question. Are we listening to what is actually said or what we expect to hear?
Something to mull over the next time you finish someone's sentence in your head. Thanks for diving in with us.
A pleasure as always.
See you next time.